Hello students, welcome to the class of Digital Signal Processing, and today we are on the third topic of our Fourier analysis. We will be studying the discrete time Fourier series today. So let's get started. What we have already done were the applications of Fourier series and transform, or you can say the application of Fourier analysis. We discussed about the scientists behind this great discovery. We also studied the basics of complex exponentials, discrete time complex exponential. How are they different from the uh, continuous time complex exponential? This is a very important thing that you have to remember, that the continuous time complex exponential are always periodic with any frequencies, and the discrete time are periodic only for rational frequencies. Means omega should be a multiple of 2 pi. Otherwise, they will have aliasing effects. And also, there is one thing, that in case of discrete time exponentials, the different exponentials are also means they are not infinite in case of as in case of continuous time. So we will see this part once more, and then we will go into the problems which we have to solve for this finding out the discrete time Fourier series. So let's get started. So first thing, that is the representation for discrete time Fourier series. So we have already done it, but let's do it once more. So what we have to do here is that, yes, discrete time Fourier series, that is DTFS. So the discrete time Fourier series is written in this form: xn. This is a discrete time signal. Discrete time signal, as you can see over here, this is n. Now this is written as k equals to 0 to n minus 1, pk e to the power j 2 pi k n by capital N. Now here, n is going from 0 to n minus 1. The counterpart of this is finding out the Ck. So Ck is equal to 1 by n. Small n is equal to n equals to 0 to capital N minus 1. Xn e to the power minus j 2 pi k small n by capital N. And here the k is going from 0 to n minus 1. So what you have to understand over here is that we have two variables, k and n. K is denoting different complex exponentials. Different complex exponentials. And n, small n, is denoting different time instants, or your sampling instance. Different time instants. And both k and n are periodic in capital N. Both k and small n are periodic in capital N. That means after every capital N interval, you will have same type of exponential, and you will have the same value of the function also. That is, at the different time instants, you will have same pk also. So what is meant by different complex exponential? How to understand this thing? Say in very simple terms, if you have a signal e to the power 2x, or you have another signal e to the power 3x. So these two are varying in what? The value of 2 and 3. So these, if you put the value x is equal to 1 over here, 2 and 3, then this is going to be denoting the n. Here, this x will, okay, I'll just give you another example graphically. So if you see it graphically, that will be much better. So see, if I draw an exponential like this, so these are different k. Say this is k equals to 0, this is k, 0 won't be there. K equals to 1, this is k equals to 2, this is for k equals to 3. And these are the different time instants. So this is your n. So this is for 1, this is for 2. So here also you will have that 1. Here also you will have that 2, 3, 4. So this is the meaning of different complex exponential and different time instants. So this is not only periodic in the time instants, it is also periodic in different in the different complex exponentials, or you can say in different k. Now this part of it, this ck is called the Fourier series coefficient. Ck is called the Fourier series coefficient. This is your original signal xn. So with the when you are decomposing the signal into its Fourier series, that is will be represented by ck. Again, if you want the signal back from it, then you have to use this method. Ck into e to the power j 2 pi k n by n. So this is the full meaning, or you can say this is the inverse Fourier inverse DTFS, and this is the DTFS. We don't use these words for the series case, but if you compare it with, or you make it analogous to the transform case, then you can speak like that this is the discrete time Fourier series and this is the inverse of the discrete time Fourier series. Basically, when you get back the function or the function in time domain, then that case we call it xn, and if you want the function in the frequency domain, then we call it ck. So it's pretty clear now. After this, there are two things that you have to remember. That is the varying of the frequency over the magnitude of the frequency over time, that the magnitude of the frequency over frequency. So this ck is having two parts. One is the magnitude part of it, and the other one is the phase part, angle of ck. So this one, when mod of ck versus omega we plot, that is called the magnitude spectra. That is called the magnitude spectra. And when we plot angle of ck versus omega, that is called the phase spectra. Now, there is a property for the magnitude and the phase spectra. That is ck, mod of ck is equals to mod of c minus k. That means if you are taking the negative of k, that is equal to ck, right? And if you take ck, angle of ck, that will be equals to minus of c minus k. So the spectra, the magnitude spectra, this is the magnitude spectra with respect to omega. This will be the magnitude spectra with respect to omega. Same case this way. So this is an even function of k or omega, and this one is an odd function. So magnitude spectra is an even function, and the phase spectra is an odd function. This symmetry property, you should remember. So till now, what we studied was, we are studying discrete time Fourier series. So discrete time, the signal has to be discrete in time. So we are taking this xn. Now we want to analyze the frequency part, or we want to find out the frequency part of this signal. How we will get the frequency part? We will get the frequency part by using this ck. We are denoting the frequency part with ck. And the formula we use to calculate the frequency part is 1 by n equals to 0 to n minus 1, xn e to the power minus j2 pi k n by n, where k is ranging from 0 to n minus 1. Fine. Now, if we want the original signal back, that time we need to use this formula, that is xn is equal to, original signal was what? Xn, and the Fourier representation for this was ck. So these are the formula. Here we had two different variables, k and small n, small k and small n, and this capital N. So capital N is basically the time period or the fundamental period, And this small k is denoting your different complex exponentials, and small n is denoting different time instants. And the beauty of this is that both k and n are periodic in capital N. I explained you what is the actual meaning of this changing of k and changing of n with the help of this diagram. Changes means the full exponential, the complete signal changes, and n changes means the sign changes, right? Now we also saw how the magnitude, this was the frequency spectra. So frequency spectra is having two parts. Frequency spectra will have magnitude spectra and phase spectra. That is, Ck will have mod Ck and angle of Ck. So this is the way how we will get it. That is very easy. So you have the complex signals, complex signal you have studied. So complex signals, or you can say complex functions. For that, how you take out the magnitude, same way. And here tan inverse of imaginary part by omega, and here it will be modulus of real part ka whole square plus imaginary part ka whole square. Now let's go and do some actual questions. So what can be the questions over here is, find the spectral coefficients. So first question that we will be doing is, find the spectral coefficients for xn is equal to cos pi n by 4. So one way of doing this is to find what is this first. First of all, let us understand what is this spectral coefficient. Means they are telling you to find out secret. Now we know the formula, but we will be doing it with another method, because by using the formula, it is going to become longer. So let's understand how to do it. We will be using the Euler's form, right? Okay. So here you know that e to the power j omega n, Euler's formula, which says cos omega n plus j sine omega n. If I want, and if you have e to the power minus j omega n, that can be written as cos omega n minus j of sine omega n. Now, I'll be doing this for one time. Now, for the rest time, we will be directly using it. Okay, so just understand this. If I add these two, e to the power j omega n plus e to the power minus j omega n, then what will happen? Plus j omega n minus j omega n will cancel, and in this side, 2 cos omega n. So divided by 2, this will be equal to cos omega n. Similarly, if I subtract 1 and 2, this is my 1, and this is my 2. We have got this by adding 1 and 2. By adding 1 and 2. If I subtract 1 and 2, then what will I get? If I subtract 1 and 2, then what I'll get is, this side I'll get 2j sine omega n, and this side I'll get e to the power j omega n minus, so I will be getting sine omega n is equal to e to the power j omega n minus e to the power minus j omega n divided by 2j. Fine. Now using this thing in this case, in my question is xn is equal to cos pi by 4n. So my question is xn is equal to cos pi by 4n. So I can write this as e to the power j pi by 4n plus e to the power minus j pi n by 4 divided by 2. Got it? This is my xn. Now, if you compare with the formula of xn, what was it? Ck e to the power j 2 pi k n by n. And here, it was varying from k equals to 0 to n minus 1. Right? Now, we will compare these two. This one, let us take it as 1, and this one, let us take it as 2. So, First of all, we need to understand that what is our time period for this signal. So the signal was given as cos pi by 4n. What is the time period for this signal? Or the fundamental time period will be written by n is equal to 2 pi by omega naught into small m. This is how we find out the time period for discrete time signals. So omega naught in this case is pi by 4. Fine. So now this pi gets cancelled, it is 8. So the smallest value of m that is going to do it, and that is going to make this an integer is m equals to 1. So our n is equal to 8. Now here you see the signals that we have, that one is signal, if you just write it individually, this one is e to the power j pi n by 4 divided by 2, and this is e to the power minus j pi n by 4 divided by 2. So what we will do is we will take the interval by using some minus part also and some positive part also of k. So let us do, but the whole range we will keep till 8. So what I'll do is, and also we have to analyze these things. Now here you see one more thing, that this is kn. See, this portion, if I write it again over here, just see, let me take a different color. So this part, this is half is the 1 by 2 if you take. So 1 by 2, and this is written as e to the power j pi n by 4. Okay, now this half is your amplitude, and this part over here, e to the power j pi n by 4, if you compare this e to the power j pi n by 4 with this part, okay, then what will you get is e to the power j, I'm writing the full thing over here, 2 pi k n by n. This is it. Now if this n I make it 8, then this becomes 4 j pi by 4, which is already there. So from here, what you can say that k is equal to 1. K is equals to 1 is there. Same way, everything is same here. So this one, for this one, it is k equals to minus 1. And for this one, it is k is equal to 1. And capital N, we already got it as 8, right? So now our thing is that we have to include the minus part and the positive part, and also we need to include minus 1 and plus 1. So what I can do is I will take the interval k equals to, say, minus 3, from minus 3 to 4. I am equally balancing it, nothing else. K is equals to minus 3 to 4, ck e to the power j 2 pi k small n by capital N. And the n is varying from 0 to n minus, and capital N is 8, and here it is varying from n minus 0 to n minus 1. Now just see. Now we will write the final thing. It was half. We will just rewrite it, whatever we have got here. Half this one, this portion, e to the power j pi n by 4. So xn is equal to e to the power j pi n by 4 plus e to the power minus j pi n by 4 whole divided by 2. So this one we will write now. Xn is equal to half e to the power j pi n by 4 plus half e to the power j minus j pi n by 4. If I now write it as this, k equals to minus 3 to 4 tk e to the power j pi by 4 n into 1. So this is k basically. So for k equals to 1 and k equals to minus 1, ck, this ck is playing the same role as half here. So ck equals to half. So c of 1 equals to half, and c of minus 1 equals to half. For all the rest of the values between minus 3 to 4, for rest k, k, ck is equals to 0. Rest k here means from in between k equal to -3 to 4 only, except k equal to 1, except k equal to 1 and minus. Got it? So the spectral coefficients will be that will be for ck is equal to half, for k equal to -1 and +1. So let's do one more question on this. Okay. So the next question is, find the DTFS representation for xn equals to, find DTFS representation for xn equal to 5 plus sin n pi by 2 plus cos n pi by 4. So first step, always remember, in the previous question we did it in a hurry. Let us do it stepwise. Step 1 will be finding the time period, finding fundamental time period, or you can say fundamental period itself. First thing we will do is finding the fundamental period. So for this one, this is a constant, so period is not required here. For this one, if you see n is equal to n1, we will write here 2 pi by omega naught. Omega naught is pi by 2 into small n. And then for the other one, n2 will be 2 pi into 4. Again, we can take a different thing over here. Let's say n only here also we take. Then it is 4 for this one, for m equal to 1. And for this one, it will be 8 for m equals to 1, smallest value. Now 4 and 8, these are two different, so we will take the LCM of 4 and 8. That will give me 8. So capital N will be 8 for our case. Now we will rewrite the signal. Now we will rewrite the signal in this with the help of the Euler's formula. Step 2, write the signal in the Euler's formula. So 5 plus, okay, I'll write the signal as it was. So xn equals to, what was given to us was xn equals to, so I'll write it in that way itself. Xn is equals to 5 plus sin n pi by 2, 5 plus sin n pi by 2 plus cos n pi by 4. So this one will be written as 5. This is constant, so e to the power 0 will be multiplied. Here this one you see, e to the power j n pi by 2 plus e to the power j minus n pi by 2, right? Minus j n pi by 2 divided by what? This is sine, so divided by 2j. The cos one will be divided by just simply 2. So what will be there for cos n pi by 4? E to the power j n pi by 4 minus e to the power minus j n pi by 4, right? So for this one, it is going to be e to the power j n pi by 4 plus, sorry, minus e to the power minus j n pi by 4 divided by only 2. Now comparing with the standard form. Now step 3 is comparing with the standard formula. Standard formula. So what was our formula? You can write it as xn is equals to a equals to 0 to n minus 1 ck e to the power j 2 pi n by n, right? ck e to the power j 2 pi k n by n. For us, the case n is equal to 8. So e to the power j 2 pi k into n by 8. Now this gets cancelled, it becomes 4. So you are writing it as e to the power j 2 pi n by, sorry, e to the power j pi n by 4 into k. In this case, you can see it is what? For this one and this one, k is equal to 1. So k equals to 1 and k equals to minus 1 for these two, right? Because it is e to the power j n pi by 4. N is there, pi by 4 is there. N is there, pi by 4 is there. The k value is 1 and minus 1. For this case, what should be the value so that you get 2 over here? So if you put k equals to 2 and minus 2, what you will get is e to the power j n pi by 2. In this one, if you put k equals to 2, then what will you get? E to the power j pi n by 2, which is here. So this is for k is equal to 2 and this is for k equals to minus 2. Now, since the things that we need to incorporate is k is equals to 0, minus 1, 1, minus 2 and 2, and capital N is equal to 8 for us. So what we will do is we will take the same thing, the interval that was k equals to minus 3 to 4, ck e to the power j pi n by 4 into k. Now, what happens is by comparing, we get that we have C0, that is for k equals to 0, C0 is equal to 5. C1 we have C of minus 1, we have C of 2, and we have C of minus 2. The rest value, that is minus 3, plus 3, and 4, they are 0. So what is C1? Just see C1 over here is the amplitude of this one, that is half. The amplitude of this one, half and minus half. So C1 is half and minus half. C1 is half. C of minus 1 is also half, right? Now C2 is 1 by 2j and C of minus 2 is minus 1 by 2j. Just see the coefficients over here, you will understand. So here I have done a small mistake itself, yeah. So this part over here, this will be minus, and this part over here, it is going to be plus because you're adding for cos and you're subtracting for sine. So for subtraction, minus is here. So minus 1 by 2j plus 1 by 2j. This one is 1 by 2. This is plus 1 by 2. So for both of these, you have half and C of 1 and C of minus 1. And for C of 2 and C of minus 2, you have 1. For 1 C of 2, you have 1 by 2j. And for C of minus 2, you have minus 1 by 2j. So if you plot this, if you're going to plot this, how is it going to look? Let us just see that also. So if you see, this is my omega and this is my mod of ck. Again, you have to understand that we have to plot both the magnitude and the phase spectra. So the magnitude is present for 0. For 0, we will put 5. Again, it is present for 1, minus 1 and 2 and minus 2. So for 1, it is half. This is for 1. This is for 0. For minus 1 also, it is half. For 2, also the magnitude is half, right? If you take the mod of this one, mod of 1 by 2j, if you take the mod of 1 by 2j, that is going to be half. So for 2 also it is half, and for minus 2 also it is half. And rest of the values is 0. This is the magnitude spectra. For the phase spectra, if you draw it, you will have this as C angle of ck versus omega. Here you see there is no angle, there is no imaginary part, only 5 is there, no imaginary part, no imaginary part. Here there is an imaginary part and here there is an imaginary part. So what is the imaginary part? How you know? That is presence of j. So j is present in the denominator. If you take the complex conjugate and multiply 1 by 2j, 1 by j is there. So if you take j into j, that is going to become minus j. J square means minus 1. So minus j is actually how much? It is minus pi by 2. And if you take this one, it is how much it will, this one will be? For c of minus 2, what will that be? For c of minus 2, it is going to be half. Because here you have already minus sign over here. So minus 1 by j if you take, then it is going to be half. Minus 1 by j into j into j. So this j square will become minus 1 and this one will be minus j. So again this minus gets cancelled. Here you have just j and for this case you had minus j. So what happens is you had two angles in the phase spectra. You have points at 2 points places. One was at minus 2, which is pi by 2, and other one was at plus 2, which is minus pi by 2, the angles. Otherwise, at other points, it is 0. So there is no angle here, no angle here, no angle here. All the values are 0. So the values are present only at minus 2 and plus 2 for the phase spectra. Thank you, everyone. In the next class, we will be just going briskly with the properties of the Fourier series, or maybe we will be just starting Fourier transform because that is explicitly mentioned in the syllabus that it is DFT only. So we'll be going a bit faster. Thank you.